The universe has a speed limit, and for 100 years we believed nothing could break it. Then one physicist did the math and proved that faster than light travel is not impossible. The equations worked, the physics was clean, the solution was perfect, and that is exactly what terrified everyone who read it. Today we find out why. Before we start, a gentle subscribe helps this channel keep growing. Now, let's begin. In 1994, a physicist sat alone at his desk, staring at the final lines of a paper he had just finished writing. The equations were clean, the logic was sound, the mathematics checked out perfectly. He read through it once more slowly, carefully, and then he put his pen down and sat very still, because he did not know whether to celebrate or be terrified. What he had just written was not science fiction. It was not speculation dressed up in academic language. It was a precise, mathematically valid solution derived directly from Einstein's own equations that described a spacecraft traveling faster than light, not bending the rules, not sneaking around them, fully consistent with the most tested theory in the history of physics. He had proven that faster than light travel was not forbidden by the laws of the universe, and that should have felt like the greatest discovery in human history. Instead, it felt like opening a door and finding another locked door behind it, except this one was stranger, heavier, and built from materials that might not exist anywhere in the observable universe. That tension between what the mathematics permits and what reality allows is where this story begins. And it begins long before 1994. Look up on a clear night, find the brightest star-like point in the southern sky. That is Alpha Centauri, part of the closest star system to our own. The nearest individual star in that system, Proxima Centauri, sits at a distance of 4.2 light-years from Earth. That number sounds manageable. It is not. Light itself, traveling at 300,000 kilometers every single second, takes 4 years and 2 months to cover that distance. Our fastest spacecraft ever launched, Voyager 1, has been traveling for more than 45 years and has barely left our own solar neighborhood. To reach Proxima Centauri at that speed would take approximately 70,000 years. Not 70,000 years of engine time, 70,000 years of actual time passing on Earth while the ship crawls through the dark. That is the scale of the problem, not a gap we can bridge with better fuel or a more efficient engine. A gulf so vast that even light, the fastest thing in the universe, needs years to cross it. Humans have always responded to impossible distances by building faster vehicles. We crossed oceans that once swallowed explorers whole. We punched through the sound barrier that engineers once believed would tear any aircraft apart. We broke free from Earth's gravity with machines assembled from metal and burning fuel. Every generation faced a limit that the previous generation called permanent, and every generation found a way through. So the instinct when confronting the distance to the stars is to ask the same question: how do we go faster? And for most of human history, that instinct served us well, because most limits were engineering problems. They were walls built from insufficient knowledge or insufficient technology, and knowledge and technology can always improve. But the speed of light is something else entirely. It is not a wall built from ignorance. It is not a barrier waiting for a smarter engineer or a more powerful fuel source. It is woven directly into the fabric of space and time themselves. It does not sit in front of us like an obstacle to be moved. It sits beneath us, beneath everything, as part of the foundation on which reality is constructed. And here is what makes this genuinely unsettling for most of scientific history. We did not fully understand how deep that foundation goes. We knew the speed of light was a limit. We had equations that said so. But the true depth of that limit, how many layers of physics reinforce it, how many separate principles converge to hold it in place, that understanding only came from decades of physicists doing something remarkable. They tried seriously and rigorously to find a way around it. Not because they expected to succeed, because the attempt itself teaches you something. Every time someone designed a clever theoretical workaround, the universe pushed back, not with one objection but with several. And each objection came from a different corner of physics. Energy, quantum mechanics, causality, stability. They formed a kind of interlocking defense, each principle supporting the others, each one stepping forward whenever the previous one was challenged. That pattern is the real story here, not whether faster than light travel is possible, but what it means that every serious attempt to achieve it reveals something new and profound about how reality is put together. This is not a story about failure. It is a story about depth, about a universe that turns out to be stranger, more tightly constructed, and more philosophically remarkable than even the scientists who discovered its rules initially imagined. The speed of light is not just a number, it is a signal. And learning to read that signal is one of the most important things physics has ever done. To understand why this particular limit is different from every other limit humanity has ever faced, we have to go back, not to a laboratory filled with expensive equipment and teams of researchers, but to a small patent office in Bern, Switzerland in 1905, where a 26-year-old clerk was spending his lunch breaks quietly dismantling 200 years of accepted physics. If you knew with absolute certainty that a limit could never be broken, would you still keep trying? Think about that, because the answer might reveal more about the nature of discovery than the limit itself. And to understand how a speed limit becomes something far more fundamental than a rule, we need to follow that 26-year-old into the strangest thought experiment in scientific history. Because what he found did not just explain why nothing travels faster than light, it revealed why space and time themselves had to be something completely different from what anyone had ever imagined. He was not famous. He was not a professor. He had no laboratory, no research budget, no team of assistants. In 1905, Albert Einstein was a 26-year-old examiner at the Swiss Federal Patent Office in Bern, reviewing other people's inventions for a modest salary. His job was to assess whether technical descriptions were logically consistent, whether the claim on paper matched the physics of reality. The irony is almost too perfect, because in his spare time, working alone, he was about to discover that reality itself did not match the description humanity had been using for 200 years. The problem that consumed him was not new. It had been sitting inside physics like a splinter for decades, ignored by most, quietly irritating the few who noticed it. James Clerk Maxwell, the Scottish physicist who unified electricity and magnetism into a single elegant theory in the 1860s, had also produced something unexpected as a byproduct. His equations predicted that light travels at a fixed speed approximately 300,000 kilometers per second, and that this speed does not depend on the motion of the source or the observer. That sounds unremarkable until you think about it carefully. Imagine standing still and watching a car drive toward you at 100 kilometers per hour. Now imagine running toward that car at 10 kilometers per hour. From your perspective, the car approaches at 110 kilometers per hour. Velocities add. That is how motion works. That is how it has always worked. Newton codified it. Common sense confirmed it. Centuries of experience agreed. But Maxwell's equations said light refuses to behave this way. If a beam of light is traveling toward you, it moves at 300,000 kilometers per second relative to you, whether you are standing still, running toward it, or flying away from it at half that speed. The number does not change. The light does not care about your motion. It simply arrives at the same speed regardless. This was deeply strange, and physicists knew it. The assumption at the time was that there must be some invisible medium filling all of space, they called it the ether, through which light traveled like sound travels through air. If the ether existed, then Maxwell's equations described light speed relative to that medium, not relative to any arbitrary observer. The strangeness would dissolve. Physics would be consistent again. So, Albert Michelson and Edward Morley built an extraordinarily sensitive instrument designed to detect the ether by measuring tiny differences in the speed of light, traveling in different directions as Earth moved through it. They worked meticulously. They minimized every possible source of error. They ran the experiment multiple times across different seasons as Earth moved along different parts of its orbit. They found nothing. No difference. No ether. No variation in the speed of light whatsoever. The universe had simply refused to cooperate. Most physicists responded by adjusting their models, adding mathematical corrections to explain away the null result while preserving the idea of the ether. Einstein responded differently. He accepted the experimental result completely and asked what it actually meant, not for the ether, but for the nature of space and time themselves. His reasoning was clean and ruthless. If the speed of light must remain the same for every observer, regardless of their motion, then the things we previously thought were fixed space and time must be the things that adjust instead. not as a trick or an approximation, as a fundamental feature of how the universe works. The consequences were staggering. Two people moving at different speeds do not just measure distances differently, they genuinely inhabit different versions of time. A clock moving through space ticks more slowly than a clock at rest, not because of vibration or mechanical interference, because time itself passes more slowly for objects in motion. The faster you move through space, the slower you move through time. At everyday speeds, the effect is so small it is unmeasurable without atomic precision. But at significant fractions of the speed of light, it becomes impossible to ignore. This is not a thought experiment, it is a measured reality. The global positioning system, the network of satellites that powers every navigation application on every phone on the planet, depends on extraordinarily precise timing signals transmitted from orbit. But those satellites move at significant speeds relative to the surface of Earth, and they sit at a different depth in Earth's gravitational field. Both effects, one from special relativity and one from general relativity, cause the satellite clocks to drift relative to ground clocks. The drift is small, a handful of microseconds per day. But in terms of positioning, a few microseconds of timing error translates to several kilometers of location error. Every day, the system corrects for these relativistic effects automatically. Without those corrections, GPS would become useless within hours. Every time a navigation app guides someone accurately through an unfamiliar city, it is silently applying Einstein's equations. Relativity is not a distant abstraction. It is infrastructure. And the deeper implication, the one that matters for everything that follows, is that space and time are not the stable, independent background against which events unfold. They are dynamic. They bend. They stretch. They compress. They are part of the physical universe, not merely the container for it. And anything that is part of the physical universe can, in principle, be shaped. That insight would eventually become the seed of something extraordinary. But first, it produces a paradox. If time slows for moving objects and space contracts in the direction of motion, what happens as speed increases toward the speed of light? The answer is where the real wall appears, not as a sign saying forbidden, but as a mathematical structure that makes crossing it literally meaningless. Here is something worth sitting with. If time genuinely runs at different rates for different people, depending on how fast they are moving, then right now, someone on a fast-moving aircraft is aging very slightly more slowly than someone sitting still on the ground. Not metaphorically, actually. What does that do to your intuition about time? As something shared and absolute, time bends, space bends. These are measured facts, not poetic metaphors. But the same equations that reveal this flexibility also reveal something else. A hidden trap encoded in the mathematics that makes the very act of accelerating toward the speed of light increasingly then infinitely costly. And it is in that cost structure where the real nature of the limit reveals itself. There is a version of this story that goes, if you want to travel faster than light, you just need a powerful enough engine, a big enough fuel tank, a sufficiently advanced civilization willing to invest the resources. That version is wrong, and the reason it is wrong is more interesting than the version itself. The barrier is not technological. It is not about the gap between what we can build today and what we might build in 1,000 years. It is mathematical. It is structural. It is a consequence of the same equations that correctly predict every electromagnetic phenomenon we have ever measured, that accurately describe the bending of light around massive objects, that allowed engineers to build a satellite navigation system that works to within meters anywhere on Earth's surface. Those equations say something very specific about what happens to an object as it accelerates. At low speeds, the energy needed to go faster scales in a simple and familiar way. Double the speed, quadruple the energy. Triple the speed, multiply the energy by 9. This is the relationship from classical physics, and it works well enough for rockets, aircraft, and everything else we build. But as speed approaches a significant fraction of the speed of light, this relationship begins to change. The curve steepens. The energy required grows faster than the speed itself. At 10% of the speed of light, the energy requirement is already large, but still in principle imaginable. At 90%, the numbers have become extreme. At 99% of the speed of light, reaching that speed would require energy equivalent to approximately 7 times the rest mass energy of the entire spacecraft. Every atom of it converted completely into pure energy, nothing left, just to move the now non-existent ship to that velocity. At 99.9999% of the speed of light, the multiplier has grown into the thousands. And at exactly the speed of light, not 99%, not 99.9, but the actual value, the energy required, becomes infinite. Not very large, not beyond current technology. Infinite, in the precise mathematical sense of the word. A quantity without bound, without limit, without any finite value that can be assigned to it. Infinite energy does not exist. It cannot be stored. It cannot be produced. It cannot be gathered from any finite region of space. The universe does not contain it. This is not a technological limitation waiting to be overcome by a more advanced civilization. It is a statement about what numbers are allowed to exist in reality, and the statement is absolute. Here is what makes this genuinely strange. The barrier does not announce itself from a distance. There is no point at which an accelerating spacecraft hits a wall and stops. Instead, the universe makes it progressively, then prohibitively, then infinitely harder to go faster. Like climbing a mountain, where the slope increases gradually, then dramatically, then becomes perfectly vertical, and then keeps going, curving back over your head, so that the summit is not just unreachable, but definitionally above any finite altitude. You could convert every star in the Milky Way into pure energy. Every single one, hundreds of billions of stars, each one millions of times more massive than Earth, every atom of each one released as pure fuel. The equations would look at that number and say, not enough, not even close. The speed of light would still sit at the same mathematical distance, unreachable, not because the number is large, but because the number required is infinite, and infinity is not a number you can reach by adding finite quantities together, no matter how many. This is the first layer of the limit, not a rule written into the universe from outside, a consequence that falls directly from the observed behavior of light and the structure of space and time. Remove the speed limit and you have to explain why light behaves the way it does, and the only available explanation produces the limit again. It is self-reinforcing at the foundation level, but here is what matters most about this layer. It is only the first one. Because the speed of light is not defended by a single principle. It is defended by several, each one independent, each one coming from a different part of physics, each one capable of standing alone, even if the others were somehow removed. Energy is the most visible defender, the most intuitive, the one that translates most directly into practical terms. But energy is not the deepest reason. It is the outermost layer of a much more elaborate structure. The deepest reason, the one that would survive even if somehow impossibly the energy problem was solved, lies not in thermodynamics or particle physics, but in the logical architecture of cause and effect itself, in something so fundamental that without it the word physics would cease to have meaning. In something, the universe appears to protect not just passively through the difficulty of achieving high speeds, but actively through cascading consequences that strike down any approach from any angle. That something has a name, and understanding it changes everything about how we read the speed limit, not as a prohibition, but as a load-bearing wall holding up the entire structure of reality. There is a wall that cannot be broken by any amount of force or energy or ingenuity. Not because we lack the tools, but because the wall is made from the same material as the rules that make tools possible. What does it mean to live in a universe with a limit like that? And does knowing it change anything about what we do next? Infinite energy cannot move a spacecraft to the speed of light. That much is certain. But the reason the universe enforces that limit so absolutely, the reason every path toward it closes, goes much deeper than energy. It goes all the way down to the question of what it means for one thing to cause another. And when you follow that thread to its end, the speed of light stops looking like a restriction and starts looking like something the universe cannot afford to lose. There is a principle so fundamental to the way reality works that we rarely stop to name it. We just live inside it the way fish live inside water, never noticing it is there until someone asks what would happen if it disappeared. The principle is, this causes happen before effects. A match strikes, then fire appears. A stone leaves a hand, then a window shatters. A signal is sent, then a signal is received. The sequence is not negotiable. It is not a cultural convention or a habit of perception. It is the backbone of every chain of reasoning, every experiment, every prediction physics has ever made. Without it, the word because loses all meaning, and without because nothing in science works at all. This principle has a name, causality, and it turns out to be the deepest reason the speed of light cannot be broken deeper than energy, deeper than mass, deeper than any mechanical difficulty, because faster than light travel does not just require enormous resources. In the right circumstances, it manufactures logical contradictions so severe that the universe itself would have no consistent way to continue existing. To understand why we have to revisit something from the previous part of this story, Einstein showed that time is not absolute. Two observers moving at different speeds genuinely disagree about when things happen, not because of measurement error or limited instruments, because time itself flows differently for each of them, and both are correct within their own reference frame. This leads to something deeply counterintuitive. Two observers can disagree not just about how much time passes between two events, but about the order in which those events occur. If event A and event B are separated in space, and neither can influence the other through any signal traveling at or below light speed, then one observer might see A before B, while another moving at a different velocity sees B before A. Both descriptions are valid. Both are physically real. Neither is wrong. This sounds alarming. If event ordering is relative, does that not already break causality? It does not, and the reason why reveals exactly what the speed of light is actually protecting. The critical distinction is between events that are causally connected and events that are not. If A causes B, if A sends a signal that reaches B and produces a response, then A must come before B for every observer in every reference frame. The mathematics of special relativity guarantees this precisely because the signal connecting them cannot travel faster than light. The causal chain is preserved universally. The only events whose ordering can appear reversed to different observers are events with no causal connection, events so far apart in space, and so close together in time that not even light could travel between them. Those events cannot influence each other. They cannot be linked by any signal. And because they cannot be linked, the reversal of their apparent order has no physical consequences. No paradox arises because no cause and effect relationship exists to be violated. The speed of light is the exact boundary that separates these two categories. It is the line between events that can be causally connected and events that cannot. As long as no signal crosses that line, causality remains intact for every observer everywhere. Now allow a signal to cross that line. Allow information, or a spacecraft or anything, to travel faster than light, and watch what happens with careful attention to the mathematics. In one reference frame you send a message, and your correspondent receives it. Simply, normal, causal, but in another reference frame, one moving at high speed relative to you, perfectly valid under relativity, the same faster-than-light message arrives at its destination before it was sent. Not slightly before, measurably, unambiguously, physically before. This is not a thought experiment designed to produce a paradox for philosophical entertainment. It is a direct mathematical consequence of combining faster-than-light transmission with the relativity of simultaneity. The calculation is straightforward. The result is unavoidable. If faster-than-light signals are possible, then there exist valid reference frames in which those signals travel backward in time. Now take the next step. You receive a reply to a message you have not yet sent. The reply contains information. You read it. You use that information to decide not to send the original message. The message that generated the reply no longer exists. So where did the reply come from? This is not a riddle with a clever answer. There is no answer. The scenario contains an internal contradiction that cannot be resolved within any consistent logical framework. The reply exists because a message was sent. The message was not sent because the reply was received. The two facts cannot simultaneously be true, and yet faster-than-light communication combined with the relativity of simultaneity requires them to be. Physics does not tolerate internal contradictions. Mathematics does not either. A physical theory that permits them is not merely incomplete. It has ceased to function as a description of reality. Every prediction it makes becomes suspect because a system with logical contradictions can be used to prove anything, including its own opposite. The entire predictive structure of science depends on causality remaining inviolable. The speed of light is not simply a speed limit. It is the boundary condition that keeps the logical structure of the universe coherent. Remove it, and you do not get a faster universe. You get an incoherent one, a universe where effects precede causes, where events undermine their own preconditions, where the past becomes vulnerable to actions taken in the future. Some theorists have proposed that perhaps a fully developed theory of quantum gravity, a framework we do not yet possess, might contain mechanisms that prevent paradoxes from forming even in a faster-than-light scenario. Perhaps the universe has a self-healing property that patches logical wounds before they propagate. This idea is sometimes called chronology protection, the conjecture that physical law conspires to prevent closed causal loops from ever completing themselves. If chronology protection is real, it is not a single law. It is a tendency encoded across multiple layers of physics simultaneously. Quantum fluctuations, geometric instabilities, energy divergences, all converging to destroy any configuration that would allow the past to be altered. The universe would not just fail to permit causality violations, it would actively dismantle any structure capable of producing them before the violation could occur. That is a remarkable thing to contemplate. Not a passive limit, an active immune response. A universe that monitors its own logical consistency and eliminates threats to it before they can materialize. The speed of light from this perspective is not a wall standing between us and the stars. It is the outermost expression of a system that keeps reality from consuming itself. Every photon traveling at exactly 300,000 kilometers per second is in a sense tracing the boundary of that system. Every experiment confirming the limit is confirming that the universe's immune system is functioning, and this is why the limit feels so absolute. Not because physics is conservative or unimaginative, but because the alternative is not a faster universe. The alternative is a universe with no consistent history, no reliable sequence of events, no ground on which prediction or understanding can stand. Imagine a world where effects routinely precede their causes, where you receive the consequences of decisions before you make them, where memory and anticipation swap places, where the word before loses its meaning entirely. Hold that image in your mind. Now ask, would anything in that world be knowable? Would science be possible? Would any action have a predictable result? The universe is protected by physics and by logic, simultaneously two separate defenses that reinforce each other at every to scale. It seemed for a long time like an airtight case. Nothing moves faster than light. Nothing can. The mathematics says so. Causality demands it. The story appeared to be over, until Einstein himself, without intending to, without realizing what he had done, drew a map that pointed toward a way out of the very maze he had built. 10 years after rewriting the rules of motion, Einstein rewrote the rules of gravity. And in doing so, he quietly introduced something into physics that would take the rest of the century to fully appreciate a distinction so subtle that most people pass over it without noticing, yet so consequential that it changes everything about what is and is not possible in this universe. The year was 1915. The theory was general relativity. For more than 2 centuries before Einstein, gravity had been understood through Newton's framework, an invisible force reaching across empty space, pulling massive objects toward each other with a strength that fell off with distance. The framework was extraordinarily successful. It predicted the orbits of planets. It explained the tides. It allowed astronomers to locate Neptune before anyone had pointed a telescope at it, simply by calculating the gravitational influence it must be exerting on Uranus. Newton's gravity was one of the greatest intellectual achievements in human history. It was also, Einstein concluded, fundamentally wrong. Not wrong in its predictions at ordinary scales, those remained accurate enough for almost every practical purpose. Wrong at a deeper level, wrong about what gravity actually is. Einstein's insight was geometric rather than mechanical. Massive objects do not pull other objects toward them by exerting a force across empty space. Instead, mass and energy curve the fabric of space-time itself. Objects moving through that curved space-time follow the straightest paths available to them, and those paths in the vicinity of a massive body curve inward. What we experience as gravitational attraction is simply the geometry of space-time guiding objects along the most natural routes through it. The rubber sheet analogy appears here in almost every explanation. and it earns its place. Place a heavy ball on a stretched elastic sheet. The surface dips. Roll a smaller ball nearby, and it curves toward the depression not because the large ball is pulling it, but because the surface beneath it is no longer flat. General relativity extends this picture to 4 dimensions, with time woven into the geometry alongside the 3 spatial dimensions. The prediction was dramatic and specific. If gravity is geometry, then even massless particles, photons, particles of light, must follow curved paths through curved spacetime. Light should bend when it passes near a massive object. Newton's gravity predicted no such bending, or at most half as much. Einstein's geometry predicted a precise value. In 1919, the British astronomer Arthur Eddington led an expedition to observe a total solar eclipse. During the minutes of totality, stars near the edge of the sun became visible. Their apparent positions were shifted, bent by the sun's gravitational field, exactly as Einstein had calculated. The measurement confirmed general relativity with startling precision. Overnight, the obscure theory became front-page news worldwide. But the more consequential confirmation came nearly a century later. On the 14th of September 2015, 2 extraordinarily sensitive detectors located in the United States registered something that had never been directly measured before. A ripple in space-time itself, a gravitational wave produced by 2 black holes that had spiraled together and merged approximately 1.3 billion years ago. The collision released more energy in a fraction of a second than all the stars in the observable universe emit in that same interval. And the distortion it sent through the fabric of space-time, traveling outward at the speed of light for over 1 billion years, finally arrived at Earth and squeezed and stretched the detectors by a distance smaller than 1,000th of the diameter of a proton. The detection was a triumph of precision engineering, but its deeper significance was conceptual. Space-time is not a passive backdrop. It vibrates. It carries waves. It is as physically real and dynamically active as any substance in the universe. And that dynamic nature, the fact that space-time moves, bends, stretches and ripples, is the key to everything that follows. Because here is what general relativity reveals, that special relativity does not the speed limit applies to motion through space-time. It says nothing about the motion of space-time itself. In the earliest moments after the Big Bang, during a period physicists call cosmic inflation, the universe expanded at a rate so extreme that regions of space were driven apart faster than light could travel between them. Not because anything moved through space faster than light, but because the space between those regions was expanding, growing at a rate that outpaced light's ability to cross the widening gap. The regions themselves were not moving. The distance between them was simply increasing, driven by the expansion of the fabric of space. This did not violate special relativity. It did not violate general relativity. It violated nothing. Because the speed limit says no object moves through space faster than light, it does not say space cannot expand faster than light. Those are 2 entirely different statements. And the universe, it turns out, treats them as entirely different rules. The distinction seems technical at first, almost semantic, but sit with it carefully and its implications become staggering. If space-time is dynamic, if it can expand, contract, curve, ripple, and carry waves, then it is not merely the arena in which physics happens. It is a participant. It has its own behavior, its own degrees of freedom, its own capacity to move and change independent of whatever matter and energy it contains. And if it can expand faster than light on cosmic scales, the question that follows is almost unavoidable. Could it be shaped deliberately, locally to carry something along with it? Not to push an object through space faster than light, but to move the space around the object, to contract the space ahead and expand the space behind, so that the object arrives somewhere distant without ever locally exceeding the speed limit. The object stays still. The geometry moves. It is a completely different question from everything physics had been asking before. Not how do we accelerate a spacecraft, but how do we reshape the space-time the spacecraft sits inside? General relativity does not forbid unusual shapes of space-time. It describes how mass and energy curve it, but it does not place hard limits on how unusual those curves might be. The equations work in both directions. Given a mass distribution, you can calculate the resulting geometry. But you can also run the calculation in reverse. Start with a desired geometry, and ask what energy distribution would be required to produce it. That reversal is a door. And for decades after Einstein published General Relativity in 1915, almost no one walked through it. The tool existed, the mathematical framework was there, but no one asked quite the right question in quite the right way until someone did. Until a physicist sat down and asked not how to build a faster engine, but how to write down the equations for a bubble of space-time that moves and what it would take to make one real. If space itself can expand faster than light has been doing it since the beginning of the universe, is doing it right now in the vast distances between galaxy clusters, what does that suggest about the nature of the speed limit? Is it truly absolute, or is it more specific than we thought? A constraint on objects moving through space, not a constraint on what space itself can do. That question, quiet, precise, deceptively simple, is the thread that unravels everything that comes next. Because the answer to it is the most mathematically beautiful, physically demanding, and philosophically unsettling proposal in the history of faster-than-light research. And it came not from a dream or a lucky accident, but from a physicist who decided to take Einstein's equations completely seriously and ask what they actually permitted without assuming in advance that the answer would be ordinary. There is a particular kind of silence that falls over a room when someone says something so unexpected, so precise, and so consequential that the usual reflexes, skepticism, counter-argument, polite dismissal simply do not activate in time. The mind needs a moment to catch up, to verify that it heard correctly, to check whether the rules of the conversation have somehow changed without announcement. That silence, in written form, is what spread through the theoretical physics community in 1994. It began with a paper, not a speculative essay, not a philosophical meditation on the limits of science, not a popular article dressed in academic language. A paper with equations, submitted to the journal Classical and Quantum Gravity by a physicist named Miguel Alcubierre, a Mexican theorist who would later describe himself without embarrassment as a devoted fan of Star Trek. He had grown up watching a fictional starship cross the galaxy in days rather than millennia, powered by something the show called warp drive. The name was evocative, but the mechanism was left deliberately vague, a narrative convenience that the writers never needed to justify because the audience never expected them to. Alcubierre decided to take the question seriously, not as a fan exercise, as a physicist. The title of his paper was measured and technical: The Warp Drive Hyperfast Travel Within General Relativity. Modest enough that a casual reader might skim past it, but the content was anything but modest. Because what Alcubierre had done quietly, methodically, using the full machinery of Einstein's general relativity, was write down the precise mathematical description of a space-time geometry that would allow a spacecraft to travel between stars in days, weeks, or hours at any speed the operator chose to specify without violating a single principle of the physics that governs our universe. Not approximately, not in some limiting case or idealized scenario. Exactly. He had not designed an engine, he had designed a geometry, and that distinction is everything. The core idea grew directly from the insight that ended the previous part of this story. Space-time is not a fixed background. It is a dynamic physical entity that can curve, expand, contract, and carry things along with it. The speed limit of light applies to motion through space-time. It says nothing about what space-time itself can do. And during cosmic inflation, space-time had already demonstrated that it could move regions of the universe apart at rates exceeding the speed of light, not because anything traveled through space faster than light, but because the space between things was growing. Alcubierre asked what if that same principle could be applied locally, deliberately around a spacecraft? The answer he derived was elegant in the way that the best physics always is not simple but inevitable once you see it clearly. Picture a region of flat, undisturbed space-time. A bubble of calm geometry, ordinary in every respect, containing a spacecraft sitting effectively at rest. Now, surround that bubble with a shell of extreme curvature, a wave of distorted space-time that contracts the space ahead of the bubble and expands the space behind it. The contraction in front effectively brings the destination closer. The expansion behind effectively pushes the origin further away. The bubble riding this wave of geometric distortion advances through space without the spacecraft inside ever accelerating, ever experiencing the crushing forces of rapid motion, or ever moving faster than light relative to its immediate, local surroundings. From inside the bubble, nothing unusual happens at all. The laws of physics operate normally. Time flows at its ordinary rate. There is no sensation of speed, no time dilation relative to the cruise zone experience, no gravitational stress on the structure of the ship. A passenger could walk around the cabin, drink coffee, read a book entirely unaware that from an outside observer's perspective, the bubble carrying them is crossing light years in a time frame that light itself could not match. From outside, the bubble moves. The surrounding wave of space-time distortion propagates forward. The spacecraft arrives at its destination, having covered a distance that in flat, unmodified space would have required years of travel at light speed, except it has done so in a fraction of that time. Weeks, days, in principle, hours, and the speed of light has not been violated. Locally, at every point inside the bubble, the spacecraft is at rest. Locally, at every point in the surrounding distortion, the geometry simply curves. No single particle, no photon, no piece of matter or energy anywhere in the system moves faster than light relative to its immediate neighborhood. Special relativity remains intact. The cosmic speed limit is honored at every local scale. What changes is the global geometry. The total distance traveled, measured across the curved and distorted spacetime outside the bubble, does not correspond to the simple flat space distance between origin and destination. The ruler itself has been redrawn. And in a universe where the ruler is made of flexible geometry rather than rigid steel, arriving faster than light, can cross a flat space distance does not require breaking the speed limit. It requires reshaping the geometry that the speed limit is measured against. This was the insight that stunned the physics community, not because it was reckless or poorly reasoned, but because it was exact. Alcubierre had not approximated. He had not waved his hands at the hard parts. He had solved Einstein's field equations, precisely produced a valid metric, a mathematical description of a space-time geometry, and shown that this metric described a configuration in which superluminal travel was geometrically realized, without local violation of any known physical law. General relativity, the theory that defines how space-time curves in response to mass and energy, had not forbidden this solution. It had produced it. The paper circulated. Physicists read it. They checked the mathematics. They found it correct. And then they sat with the uncomfortable reality that one of the most rigorous theories in all of science had just provided, without apparent objection, the blueprint for a faster-than-light spacecraft. It is worth pausing here to appreciate the precise nature of what Alcubierre had and had not accomplished. He had not built anything. He had not proposed a mechanism for creating the required geometry. He had not solved the engineering challenges, the energy requirements, or the control problems. What he had done was something that in theoretical physics carries enormous weight on its own. He had demonstrated existence. He had shown that Einstein's equations contain within their solution space configurations that permit superluminal travel. The solutions exist. They are mathematically valid. They are physically describable. In the history of physics, demonstrated mathematical existence has repeatedly preceded physical reality by decades. Maxwell's equations predicted electromagnetic waves long before Hertz generated them in a laboratory. Einstein's equations predicted black holes long before astronomers confirmed their existence with direct observation. Dirac's equation predicted antimatter before anyone had detected a positron. The pattern is well established. If the mathematics of a well-tested theory says something exists, it is worth taking seriously. Alcubierre had joined that tradition. He had found something real inside the equations, not a numerical curiosity or a pathological edge case, but a coherent, stable, geometrically meaningful solution describing a bubble of space-time moving at arbitrary velocity through the universe. The physics world did not know quite what to do with it. Some researchers were immediately excited, sensing a genuine window into previously forbidden territory. Others were deeply skeptical, suspecting that the apparent loophole would close as soon as someone calculated the physical requirements in detail. A few set to work immediately on exactly that calculation, because finding a solution is only the beginning. The next question is always, what does it cost? In physics, beautiful solutions almost always present an invoice. The more beautiful the solution, the more severe the invoice tends to be. A mathematically valid blueprint for a warp drive derived from the same equations that predict black holes and gravitational waves and the bending of light around stars. Is that a breakthrough, an illusion, or something in between a window that shows you exactly where the wall is from the inside? The invoice, when it arrived, was not merely large. It described a form of payment that physics had barely begun to understand, a currency so exotic that its very existence remained contested, its maximum available quantity governed by rules that seemed designed specifically to prevent it from ever being used at the scale the warp drive required. Every solution in physics comes with a price. The question is always whether the price can be paid. When engineers design a bridge, the solution to spanning a river exists mathematically long before the first beam is placed. But the solution requires steel, and steel requires mining, and mining requires energy. And all of it requires that the quantities involved remain within bounds that reality actually permits. The mathematics is necessary but not sufficient. The physical requirements must also be satisfiable. Alcubierre's warp drive metric existed as a valid solution to Einstein's equations. The geometry was real in the sense that physics uses that word describable, consistent, non-contradictory. But the moment physicists began calculating what physical substance would be required to produce that geometry, the invoice appeared. And it described something that no laboratory had ever created, no natural process had ever produced in usable quantities, and no theory had yet explained how to manufacture at any scale whatsoever. The warp bubble requires negative energy density, not low energy, not zero energy. Negative energy, a condition in which the energy content of a region of space falls below the energy content of a perfect vacuum, below nothing, less than empty. To understand why this is so strange, it helps to think about what energy density normally means. In ordinary physics, even empty space, a perfect vacuum devoid of all matter and radiation, has a baseline energy level. It is not zero, because quantum mechanics fills the vacuum with ceaseless fluctuations, virtual particles appearing and annihilating in intervals too brief to directly observe. This vacuum energy is the floor. It is the lowest energy state that an ordinary region of space can occupy. Negative energy density means going below that floor, creating a region of space that has less energy than nothing, a region that in terms of its gravitational effect does not attract surrounding matter but repels it, a region that curves space-time in the opposite direction from any ordinary concentration of mass or energy. This is what the warp bubble demands, and the reason is geometric. The bubble requires space-time to contract ahead of it, to focus, to compress, to bring the destination closer. Ordinary positive energy does exactly this. It curves space-time inward, focusing paths, pulling trajectories together, attracting. But the bubble also requires space-time to expand behind it, to defocus, to spread, to push the origin further away. And defocusing requires the opposite of attraction. It requires something that curves space-time outward, something that gravitates repulsively, something that ordinary matter and energy simply cannot do. The equations are unambiguous on this point. The geometry Alcubierre described cannot be produced by any arrangement of ordinary positive energy matter. It requires regions of genuinely negative energy density, arranged with precise spatial structure around the bubble boundary. Without those regions, the geometry cannot be maintained. The bubble collapses, the effect disappears. So does negative energy exist? Quantum mechanics says yes, but in quantities so minute and durations so brief that the answer offers almost no practical comfort. The most famous demonstration of negative energy in a laboratory setting is the Casimir effect, first predicted by the Dutch physicist Hendrik Casimir in 1948 and experimentally confirmed decades later with increasing precision. The setup is deceptively simple. Two uncharged parallel metal plates placed extraordinarily close together, separated by a distance measured in nanometers, a few billionths of a meter. Between those plates, the quantum vacuum fluctuations are restricted. Only fluctuations with wavelengths that fit between the plates are permitted. Outside the plates, the full spectrum of vacuum fluctuations is present. This asymmetry creates a measurable difference in energy density. The region between the plates has slightly less energy than the surrounding vacuum. It has negative energy density relative to the vacuum baseline. The plates are pushed together by this effect. The force is real. It has been measured. Negative energy, in this restricted sense, is a genuine physical phenomenon. But genuine does not mean useful at the scale the warp drive requires. The negative energy density produced by a Casimir apparatus is extraordinarily small, many orders of magnitude smaller than the energy density of an atom, which is itself vanishingly small compared to the energy densities involved in ordinary chemistry, let alone astrophysics. And the region in which it exists is measured in nanometers, constrained between two physical plates that must be held in precise alignment. Alcubierre's original calculation for the energy required to sustain a warp bubble of useful size, one large enough to contain a spacecraft, produced a number equivalent to the total mass energy of a body comparable to Jupiter in the form of negative energy. Jupiter contains approximately 2 times 10 to the 27th power kilograms of mass. Converting that to energy via the mass-energy equivalence gives a number the power that dwarfs the output of the Sun across billions of years. And this entire quantity would need to exist as negative energy, not merely concentrated in a small region, but structured with geometric precision into the specific spatial profile that the bubble geometry demands. Subsequent work by researchers including Harold White at NASA refined the geometric parameters of Alcubierre's original design. By adjusting the thickness and shape of the bubble wall, White's team reduced the theoretical energy requirement by many orders of magnitude, from Jupiter mass to something more modest, though still far beyond anything. Productively, these refinements were real contributions. The geometry of the bubble matters, and a thinner, more carefully shaped wall requires less exotic matter to maintain. But even the most optimized estimates remained separated from achievability by a gulf that felt less like an engineering challenge and more like a categorical impossibility. Because the problem is not just quantity, it is consistency with the rest of physics. Quantum field theory, the framework that successfully describes every particle and force we have ever measured, except gravity, imposes strict constraints on negative energy through what are known as quantum energy inequalities. These inequalities are not assumptions or approximations. They are derived consequences of the mathematical structure of quantum fields, and they say the following: the more negative the energy density in a given region, and the larger the volume of that region, the shorter the duration for which that negative energy can exist. The relationship is not linear, it is severe. To sustain a macroscopic region of significant negative energy density for the duration required to complete even a short interstellar journey, a journey that might take days or weeks in the warp bubble's reference frame, the quantum inequalities would demand compensating positive energy, densities so extreme that they would collapse the surrounding spacetime into a black hole. The very act of trying to sustain the negative energy required to prevent a black hole would create the conditions for one. The universe, it appears, has a credit policy for negative energy. Small amounts, briefly, in microscopic regions this is permitted. The Casimir effect demonstrates it. The loan is allowed, but the moment you attempt to scale up to borrow more energy for longer, the interest rate spikes catastrophically. The universe demands immediate repayment in the form of positive energy that overwhelms the negative energy you borrowed, and the net result is always the same. You cannot accumulate enough negative energy to do anything macroscopically useful without the surrounding physics collapsing configuration before you can use it. This is the second layer of the universe's defense of its speed limit, not the energy required to accelerate a massive object that was the first layer from special relativity. This is the energy required to shape the geometry of spacetime itself, from general relativity constrained by quantum mechanics. Two completely separate physical frameworks, operating at completely different scales, both converging on the same conclusion. The warp drive's requirements cannot be met, and the convergence is not accidental. It reflects something deep about the relationship between gravity and quantum mechanics, a relationship that physicists have been trying to fully understand for nearly a century. Every time a proposed workaround exploits the geometry of spacetime in a way that seems to bypass the speed limit, quantum mechanics appears with a new constraint that closes the gap. The two theories have never been fully unified. They disagree about the nature of reality at the smallest scales, and yet they appear to cooperate with remarkable consistency in the specific task of enforcing the cosmic speed limit. The warp drive had gone from mathematically elegant to physically demanding in ways that quantum mechanics specifically prohibits. The invoice had been presented, and it asked for a currency that the universe issues only in trace amounts and immediately reclaims. If physics someday found a way to generate stable negative energy, even in small but controllable quantities, what would you do with it first? Not the warp drive, which remains far beyond any plausible application. Something smaller, something that requires just a little bit of energy below the vacuum floor. The answer might reveal more about what negative energy actually is than any theoretical paper. The negative energy problem alone seemed fatal, a requirement without a supplier. A demand the universe appears constitutionally unwilling to meet at the required scale. It would have been reasonable at this point to close the file on the Alcubierre drive entirely. Many physicists did exactly that, but others pressed forward, because even if the energy problem were somehow solved, even if some future physics provided a pathway to controlled negative energy in macroscopic quantities, a deeper and stranger problem was already waiting inside the geometry itself. A problem that had nothing to do with energy and everything to do with the fundamental impossibility of controlling something you have already placed beyond your reach. Assume for a moment that the energy problem has been solved. Assume that some future physics, some framework we have not yet written, some discovery we have not yet made, provides a pathway to negative energy in the quantities the warp bubble demands. Assume the geometric precision required to shape the bubble wall has been achieved, that the quantum inequalities have been navigated, that the invoice from the previous chapter has somehow been paid. Assume all of that, and ask the next question, does the warp drive then work? The answer is no, and the reason has nothing to do with energy. It has to do with something more fundamental, the relationship between the bubble and the crew inside it, and what the geometry of superluminal motion does to that relationship the moment the bubble crosses the speed of light. Because what the mathematics reveals at that threshold is not a technical complication to be engineered around. It is a structural feature of the geometry itself, as unavoidable as the horizon of a black hole, and equally impossible to escape from the inside. When the warp bubble moves faster than light relative to the surrounding spacetime, it creates a boundary, not a physical wall, not a material surface, a causal boundary, a surface in spacetime beyond which no signal originating from inside the bubble can travel. This boundary forms at the leading edge of the bubble, the front face of the distortion that is contracting the space ahead. And the reason it forms is the same simple, brutal logic that governs horizons everywhere in general relativity. The front edge of the warp bubble is advancing through space faster than light. Any signal emitted from inside the bubble toward that front edge, any light pulse, any electromagnetic transmission, any physical carrier of information whatsoever, travels at the speed of light relative to its local surroundings. But its local surroundings are themselves inside a bubble moving faster than light. The signal moves forward at light speed through the interior. The front edge moves forward faster than light through the exterior. The gap between the signal and the edge does not close, it widens. The signal never arrives. This is not an approximation or an edge case. It is a clean geometric consequence that follows directly from the definition of superluminal motion. A bubble moving faster than light is by construction a bubble whose leading surface is unreachable by anything originating from its interior. The front of the bubble is causally disconnected from everything behind it. For the crew inside, this has an immediate and catastrophic practical consequence. They cannot control the bubble they are traveling in. Every act of navigation requires sending information forward. You observe the space ahead, identify an obstacle, and send a correction signal to adjust your trajectory. You calculate that you have traveled far enough and send a command to begin deceleration. You detect an unexpected gravitational anomaly and send instructions to modify the bubble's shape. All of these actions require a causal chain that moves from the crew through the bubble interior to the leading edge of the geometry, the edge that is doing the actual work of contracting space ahead. But the leading edge cannot receive those signals. It is moving away faster than light. The crew's instructions chase the horizon and never reach it. Every command to steer, brake, or modify the trajectory dissolves into the causal gap between the interior and the front of the bubble. The spacecraft is no longer a vehicle. It is a sealed compartment inside a geometric wave propagating forward through space-time with no mechanism by which the occupants can influence its direction or velocity. They can observe their instruments. They can communicate with each other. They can do everything that passengers in an enclosed space can do. But they cannot drive. They cannot steer. They cannot stop. A projectile once fired follows a ballistic trajectory determined by the conditions at launch. The warp bubble, once activated at superluminal speed, is subject to the same limitation, except that the trajectory is not determined by gravity and initial velocity, but by the geometric configuration of a space-time distortion that the crew can no longer reach. Whatever course was set at the moment of departure is the course that will be followed without adjustment for the duration of the journey. This raises the stopping problem in its starkest form. At the destination, the bubble must be collapsed. The exotic energy configuration sustaining the geometry must be switched off or modified or dissipated in some controlled way that allows the spacecraft to emerge from the bubble into flat space-time without catastrophic consequences. But the mechanism for doing this lies at the boundary of the bubble which the crew cannot reach, with signals or requires modification of the space-time geometry outside the bubble which the crew cannot access at all from the inside. The proposed solution in some theoretical discussions is to build the infrastructure for bubble collapse at the destination before the journey begins. A receiver station already in place at the target star system, capable of interacting with the incoming bubble from the outside and engineering its controlled dissolution. The crew would simply wait for arrival, but this solution requires that someone or something reach the destination first by some other means, presumably slower than light, and constructed the necessary infrastructure before the warp journey was attempted, which means the first warp journey to any given destination is impossible using this approach. Only destinations already visited by slower means could be safely reached. The warp drive in this scenario is not an explorer's tool. It is a fast lane on a road that someone else had to build the long way. And even if the stopping problem was somehow resolved, the bubble's interaction with the surrounding universe during transit introduces hazards of a different and equally severe kind. Interstellar space is not empty. Between the stars, the medium is thin, far thinner than the best vacuum achievable in any terrestrial laboratory, but it is not nothing. Hydrogen atoms drift through it 1 or 2 per cubic centimetre on average. Dust grains move through it. Photons from distant stars cross it in every direction. Cosmic ray particles accelerated to extraordinary energies by supernova remnants and other violent events stream through it continuously. The warp bubble's leading edge is contracting the space ahead of it. As it advances, it encounters this interstellar medium and interacts with it. The contraction of space effectively compresses the particles and radiation in the bubble's path, sweeping them toward the front boundary. Over the course of an interstellar journey, even a fast one measured in weeks rather than years, the accumulated material builds up along the leading edge. The longer the journey and the faster the bubble, the greater the accumulation. When the bubble collapses at the destination, this accumulated energy does not gently disperse. It releases, suddenly, completely, into whatever region of space the bubble has arrived in. The calculations suggest the energy release could be devastating, not merely dangerous to the arriving crew, though it would certainly be that, but potentially catastrophic for anything in the surrounding volume of space. A planetary system at the destination would absorb this energy pulse, a concentrated burst of radiation and particle flux, with consequences ranging from severe atmospheric disruption to conditions lethal to any biosphere present. A warp drive, arrival at an inhabited world, could, depending on the journey parameters, constitute an extinction-level event for that world. This is not a design flaw that can be corrected with better engineering. It is a consequence of the geometry. The bubble must contract space ahead of it to move forward. Contracting space ahead of it concentrates whatever occupies that space. Concentrated material must go somewhere when the bubble stops. The physics of where it goes are not favourable, but the most immediate threat to the bubble may not come from outside at all. It may come from the quantum vacuum itself acting from within. In 1974, the British physicist Stephen Hawking derived a remarkable and deeply counterintuitive result. Black holes are not completely black. The intense gravitational field at the event horizon of a black hole interacts with quantum vacuum fluctuations in a way that produces a slow, but steady emission of thermal radiation, now universally called Hawking radiation, that carries energy away from the black hole over astronomically long timescales. The mechanism involves the behavior of virtual particle pairs near the horizon. In the quantum vacuum, particle-antiparticle pairs continuously appear and annihilate too quickly to be observed directly. Near a black hole horizon, one member of such a pair can fall across the horizon before annihilation occurs, leaving the other to escape as real radiation. The black hole loses energy in the process. Over timescales far longer than the current age of the universe. For large black holes, this process eventually leads to complete evaporation. The warp bubble's boundary is not identical to a black hole event horizon, but it shares critical mathematical features. It is a surface across which causal contact is severed. Quantum field theory applied to such surfaces predicts similar effects. Vacuum fluctuations near the boundary are disrupted in ways that produce radiation. The bubble's causal horizon generates a thermal bath of particles building up along the interior boundary of the bubble wall. Unlike Hawking radiation from astronomical black holes, which is too faint to detect and acts on geological timescales, the radiation inside a superluminal warp bubble may build up rapidly. Some calculations suggest it could reach intensities that are fatal to biological life within the bubble on timescales of hours. Others suggest it could destabilize the exotic matter configuration, maintaining the bubble geometry before the journey is complete, causing the bubble to collapse prematurely, stranding the spacecraft in the most optimistic scenario, somewhere in interstellar space. In the least optimistic scenario, a premature bubble collapse while traveling at superluminal speeds produces consequences for the crew and the surrounding space-time that the equations describe in terms that do not invite further elaboration. The warp drive examined in full physical detail is not merely difficult to build. It is once built and activated at superluminal speeds, dangerous to operate, impossible to steer, potentially impossible to stop, safely destructive to its destination on arrival, and self-destructive during transit through quantum effects at its own boundary. Each of these problems is independent of the others. Solving the energy problem does not solve the horizon problem. Solving the horizon problem does not resolve the radiation accumulation. Addressing the Hawking-like radiation does not touch the stopping problem. The difficulties do not form a chain that breaks if you find the weakest link. They form a web, and the web holds even if individual strands are cut. A vehicle that cannot be steered, cannot be stopped, destroys its destination on arrival, and may kill its crew before they arrive. What argument, scientific, philosophical, or otherwise, would be enough to make you step inside? And if no argument is enough, what does that tell us about the difference between theoretical possibility and practical reality? The warp drive had. You accumulated enough problems independently derived from enough separate areas of physics that many researchers concluded the concept had exhausted its usefulness as a practical proposal. The mathematics had been explored. The consequences had been calculated. The universe had responded to every approach with a different objection, and the objections showed no sign of running out. But a different generation of physicists looked at the same situation and drew a different conclusion. Not that the warp drive was impossible, but that the specific version Alcubierre had proposed was the wrong design. That the problems arose not from the concept of geometry-based travel, but from the particular geometric configuration he had chosen. That if you went back to the beginning, back to Einstein's equations, back to the question of what space-time geometries are physically achievable, and asked the question differently, without assuming negative energy was necessary, without assuming superluminal speed was required from the start, you might find something that worked. Science does not always advance by proving things possible. Sometimes it advances by systematically eliminating what is not, and finding in the process of elimination something it did not expect to find. The researchers who returned to the warp drive problem in the years after 2010 were not romantics, hoping to resurrect a discredited idea. They were theorists doing what theorists do, taking a mathematical framework seriously, exploring its solution space with rigor, and following the results wherever they led. Their starting point was a precise and honest diagnosis of why the Alcubierre metric had failed to survive contact with full physical analysis. The exotic matter requirement was the most visible problem, but it was not the deepest one. The deepest problem was that the Alcubierre drive required space-time to be shaped in ways that positive energy, the only kind we know how to produce, the only kind that demonstrably exists in the universe at macroscopic scales, cannot produce. Every known form of matter, every measurable energy distribution, curves space-time in the same qualitative direction inward, attractive, converging. The paths of particles moving through regions of positive energy density are bent toward each other, not away. The warp bubble needs the opposite in key regions. It needs space-time to defocus, to push paths apart, to expand, rather than contract to curve, in the direction that only negative energy had previously been shown to produce. The new generation of researchers asked, is this truly impossible with positive energy alone, or is it an artifact of the specific geometry Alcubierre chose? Could a different geometric configuration still achieving something resembling warp-like behavior be constructed using only physically realizable energy sources? The initial results were genuinely encouraging. Subluminal warp configurations, bubbles of curved space-time that move below the speed of light, turned out to be achievable without exotic matter. A carefully designed distribution of positive energy, shaped into a shell with the right thickness and curvature profile, can produce a region of locally modified space-time that moves through the surrounding medium at velocities below light speed. The interior of this bubble is not perfectly flat space-time, but it is significantly less curved than the exterior. Objects inside experience reduced effective distances to their destination. The geometry does real work. These configurations satisfy what physicists call the energy conditions, mathematical requirements derived from general relativity that specify what distributions of energy are physically permissible. Ordinary positive energy satisfies all of them. The subluminal warp bubble constructed from positive energy alone does not violate any of them. It is in the rigorous technical sense physically realizable in principle. It can also, unlike the Alcubierre metric, be steered. Because it moves below the speed of light, no causal horizon forms at its leading edge. Signals from the crew reach the front of the bubble without obstruction. Commands propagate forward, corrections can be made. Deceleration can be initiated from inside the vehicle. The horizon problem that made the Alcubierre drive uncontrollable does not appear. The stopping problem dissolves along with it. The radiation accumulation issue similarly diminishes. At subluminal speeds, the compression of interstellar material at the leading edge is less extreme. The journey times are longer, but the energy density is lower, and the arrival event does not concentrate into a catastrophic pulse in the same R way. On every criterion that the Alcubierre drive failed, the subluminal warp configuration performs better. The physics is cleaner, the requirements are achievable, the control problems are manageable, except for one thing: it does not travel faster than light, and that means it does not solve the original problem. A journey to Proxima Centauri at 90% of the speed of light still takes nearly 5 years. To Alpha Centauri and back takes nearly a decade. These timescales are challenging for human exploration, but not cosmically impossible, but they do nothing for travel to more distant stars, and they provide no relief from the fundamental isolation that the scale of the universe imposes. The subluminal warp bubble is a potentially interesting propulsion concept. It is not a faster-than-light drive. The names are similar, but the achievement is categorically different. The researchers who had set out to build a physically realistic warp drive without exotic matter had produced something real, something useful, something worth studying, and something that did not accomplish the goal. The energy conditions had been satisfied. The price had been that the destination remained unreachable in any practical sense. The next step was natural: push the geometry harder, find configurations that use positive energy but achieve higher effective velocities. Explore whether there are arrangements of ordinary matter and energy that, through non-linear interaction with the geometry of spacetime, produce effects that mimic what negative energy would otherwise generate. General relativity is non-linear in ways that matter here. Gravitational fields interact with themselves. The presence of one concentration of energy affects the geometry, and the modified geometry affects how other concentrations of energy behave, and those concentrations in turn further modify the geometry. This self-referential complexity means that simple intuitions, positive energy focuses, negative energy defocuses, can break down in carefully engineered configurations. Multiple positive energy distributions arranged in precise geometric relationships with each other might produce effects in the combined spacetime that neither distribution would produce alone. This is a genuine area of mathematical exploration, and it has produced genuine results. Certain combinations of matter distributions create spacetime geometries with local regions that behave differently from any of the individual components. The nonlinearity is real and exploitable, but every exploration of this space runs into the same mathematical obstruction derived from a set of results in general relativity known as focusing theorems. These theorems, proven rigorously from the structure of Einstein's equations, establish that positive energy density causes geodesics to converge. Paths through spacetime that begin parallel will, in the presence of positive energy, move closer together. The effect is cumulative and unavoidable. No arrangement of positive energy sources, however cleverly configured, can produce a sustained region in which geodesics consistently diverge, because divergence requires violating the focusing theorem, and the focusing theorem follows directly from the positivity of energy. The warp bubble in its essential operation requires geodesic divergence in the expansion region behind it. This is not a peripheral feature. It is central to the mechanism. The expansion of space behind the bubble is precisely what pushes the origin away and allows the bubble to advance. Remove the divergence and you remove the warp effect. And the focusing theorem says positive energy cannot produce divergence. The wall had reappeared. Not in the same place, not made of the same material, not described in the same language as the energy condition violations in the Alcubierre drive, but structurally the same, a mathematical result proven from first principles, establishing that what the warp mechanism requires is something that the available physical resources cannot provide. Modified gravity theories offered another avenue. Einstein's general relativity, for all its experimental success, is not the only possible theory of gravity consistent with known observations. Various extensions and modifications have been proposed, motivated partly by the desire to explain phenomena like dark energy, the mysterious, accelerated expansion of the universe without invoking an unexplained cosmological constant. Some of these modified theories alter the relationship between energy distributions and spacetime curvature in ways that make warp-like geometries easier to achieve. The problem is the same one that faces any proposed modification to general relativity. Every deviation from Einstein's equations predicts observable consequences somewhere. Mercury's orbital precession, the deflection of light by the sun, the timing of binary pulsar signals the waveforms of gravitational waves detected by LIGO. All of these provide precise measurements that constrain how far any alternative theory can deviate from Einstein's predictions. The constraints are severe. The deviations allowed are small, and a consistent pattern emerged. The modifications that made warp geometries physically easier to construct also produced deviations from general relativity that had not been observed. The more precisely a modified theory was constrained to match all available experimental data, the more closely it resembled standard general relativity in its predictions, and the less advantage it offered for warp drive physics. Every degree of freedom that made the warp geometry easier to build was a degree of freedom that conflicted with something already measured. The soliton approach offered a third path, drawing on a concept from other areas of physics. In nonlinear wave systems in water, in optical fibers, in certain quantum fields, it is possible for a wave to maintain its shape indefinitely as it propagates without dispersing or decaying. These self-sustaining wave structures are called solitons. They behave in some ways like particles. They have definite shapes. They maintain their integrity through interactions. They travel at constant velocities. If spacetime could host a soliton-like distortion with a flat interior, a propagating geometric structure that carried its bubble of calm spacetime with it as it moved, perhaps this would provide the stability and persistence that the Alcubierre metric lacked. Some soliton-like solutions to Einstein's equations do exist. They are stable against small perturbations. They propagate cleanly. They maintain their structure over indefinite distances. In every mathematical property relevant to a warp drive, they perform well, except one. They cannot be created from ordinary flat spacetime by any physically realizable process. They exist as eternal features of specific spacetime geometries, configurations that must have been present from the beginning that cannot be switched on or off, that cannot be entered or exited by a spacecraft originating in flat space. They are roads that exist in the equations but have no on-ramps. Each approach had arrived at the same destination by a different route, a solution that was mathematically valid but physically unreachable, or physically reachable but not superluminal or superluminal, but requiring resources that quantum mechanics specifically prohibited or requiring modifications to general relativity that observations specifically ruled out. The pattern was not coincidental. It was a signature, the repeated imprint of a structure deeper than any individual theorem or energy condition. A structure that expressed itself in different mathematical languages depending on which approach was used to probe it, but always communicated the same essential message. When every new solution reveals a deeper problem, when the maze seems to regenerate itself every time an exit is found, is that a sign that the maze has no exit, or a sign that we are not yet asking the right question? The history of physics suggests both answers have been true at different times. The hard part is knowing which situation you are in. The maze had been mapped thoroughly enough by enough independent researchers, using enough different mathematical tools that its outlines were becoming clear, and those outlines were not the outlines of an engineering challenge waiting for better technology. They were the outlines of something much more fundamental, a structure woven through physics at multiple levels simultaneously, each level independently supporting the same conclusion, the whole system forming not a single barrier, but a landscape. A landscape that, when viewed from sufficient altitude, began to reveal not frustration but information. Not a dead end, but a map of something the universe was trying with considerable insistence to communicate. Step back far enough from any landscape, and the details dissolve. Individual trees become forest, individual waves become ocean, individual obstacles become terrain, and when you step back far enough from the decades of warp drive, research from the energy calculations and the quantum inequalities and the horizon problems and the soliton dead ends and the modified gravity constraints, what you see is not a collection of separate failures. You see a shape, a consistent, repeating, unmistakable shape that no single researcher designed and no single paper described, but that the entire body of work taken together reveals with the clarity of something that was always there, waiting to be read. Every serious attempt to achieve faster than light travel encountered resistance. That much was expected. What was not expected, what took decades of cumulative work to fully appreciate, was the character of that resistance. It was not random. It was not arbitrary. It did not come from the same place twice. Each time a theoretical approach resolved one objection, the next objection came from a completely different region of physics, derived from completely different mathematical principles, resting on completely different experimental foundations. Begin with the most visible barrier, the energy requirement of special relativity. To accelerate an object with mass to the speed of light requires infinite energy. This follows from the structure of space-time as Einstein described it in 1905. It is a consequence of how velocity, mass, and energy relate in a universe where the speed of light is constant for all observers. Address this by proposing not to accelerate through space-time, but to move space-time itself. The Alcubierre insight and the first barrier steps aside. The approach is geometrically valid. Special relativity is locally satisfied at every point. The second barrier appears immediately. The geometry requires negative energy density, and quantum mechanics restricts negative energy through the quantum inequalities. The amounts permitted are microscopic, the durations vanishingly brief, the scaling laws catastrophically unfavorable. Address this by redesigning the bubble geometry to minimize the exotic matter requirement, as Harold White and others attempted, and the second barrier retreats slightly but does not disappear. The requirement shrinks but remains physically unachievable. Suppose it was somehow met. The third barrier arrives from an entirely different direction, the causal horizon that forms at the bubble's leading edge when it moves faster than light. This is not an energy problem. It is a geometric and causal problem. The crew loses all ability to control the bubble's trajectory. The horizon is a direct consequence of superluminal motion interacting with the causal structure of space-time, and it cannot be engineered away without abandoning the superluminal motion itself. Address this by exploring subluminal warp geometries that avoid the horizon, and the third barrier dissolves, but the superluminal capability dissolves with it. The fourth barrier lives in quantum field theory, applied to curved space-time, the Hawking-like radiation that accumulates at the bubble boundary, potentially destabilizing the exotic matter configuration or irradiating the crew before arrival. The fifth emerges from the focusing theorems of general relativity, which establish that positive energy cannot produce the geodesic divergence the warp mechanism requires. The sixth arises from experimental constraints on modified gravity theories that might otherwise provide a workaround. The seventh appears in the impossibility of creating soliton-like warp geometries from flat spacetime using any physically realizable process. 7 distinct barriers, 7 independent objections, each derived from a different theoretical framework, each supported by its own body of experimental evidence, each capable of standing alone, even if all the others were somehow resolved. This is not what a coincidence looks like. This is not what a temporary engineering obstacle looks like. This is what a structural feature of reality looks like, a feature so deeply embedded in the foundations of physics that it expresses itself independently in every theoretical language available, like a single architectural fact that reveals itself in the load-bearing properties of every wall-in. A building, regardless of what material each wall is made from, the pattern carries information. Specifically, it reveals something that neither general relativity nor quantum mechanics had fully disclosed on their own. A deep and previously hidden relationship between the two theories, expressed through their shared commitment to preventing causality violation at any cost. General relativity and quantum mechanics are, in the technical language of physics, not reconciled. They rest on different mathematical foundations. They make incompatible assumptions about the nature of space and time at the smallest scales. Every serious attempt to unify them into a single coherent framework, string theory, loop quantum gravity, and a dozen other approaches, has produced partial results, mathematical insights, and unresolved tensions, but not a complete and prior, experimentally confirmed theory of quantum gravity. The two pillars of modern physics do not fit together cleanly, and that incompatibility is one of the deepest unsolved problems in science. And yet, when it comes to the specific question of faster-than-light travel, they agree completely. General relativity prohibits the required space-time geometries through energy conditions and focusing theorems. Quantum mechanics prohibits the required energy distributions through quantum inequalities. The causal structure that faster-than-light motion would destroy is protected simultaneously by both frameworks from different directions, using different mathematics arriving at the same conclusion. This agreement is remarkable, precisely because it is not expected. Two theories that disagree about almost everything at the quantum gravity scale nonetheless conspire with perfect consistency to enforce the same cosmic speed limit. Their apparent incompatibility does not extend to this question. On this question, they speak with one voice. The Warp Drive research program, in its decades of exploration, had accidentally performed something extraordinarily valuable. It had probed the boundary between general relativity and quantum mechanics and found at that boundary unexpected coherence. The attempts to violate causality had revealed through their consistent failure that causality is protected not by one theory, but by both acting in concert, as if the two theories, despite their other disagreements, had reached a prior agreement on this particular point. Stephen Hawking formalized the intuition behind this pattern in his chronology protection conjecture proposed in 1992. The conjecture states that the laws of physics do not permit the formation of closed time-like curves, paths through space-time that loop back on themselves, allowing travel into the past. Faster-than-light travel combined with the relativity of simultaneity can be used to construct such loops given the right sequence of journeys. The conjecture proposes that whenever a physical process approaches the conditions that would generate a closed time-like curve, quantum effects diverge, energy densities, blow up geometries, destabilize configurations, collapse before the loop can close. The universe, in other words, does not merely fail to provide the resources for causality violation, it actively intervenes to prevent any configuration that would produce one. The intervention is not governed by a single law or a single mechanism. It is distributed across the full structure of physics, emerging wherever it is needed, in whatever theoretical language is relevant to the situation at hand. There is something almost funny about this if you step far enough back to see the absurdity clearly. The universe does not post a single guard at the door and trust that one guard to turn everyone away. It runs an automated detection system that operates in every corner of physics simultaneously, that catches every approach from every angle, that responds to each new theoretical workaround with a freshly derived objection from a completely different branch of science. It is the most thorough and redundant security architecture imaginable, and it was never designed by anyone. It just turned out through the accumulated structure of physical law to be exactly what was needed to keep space-time coherent. The image that comes to mind is not a wall, it is something more like an immune system. A biological immune system does not defend the body through a single mechanism. It operates at multiple levels: physical barriers, chemical signals, cellular responses, molecular recognition, each layer independent, each capable of responding to threats. The others might miss the whole system far more robust than any individual component. Pathogens that defeat one defense encounter another. Those that defeat two encounter a third. The redundancy is not inefficiency. It is the point. The universe's defense of its speed limit has exactly this character. Energy requirements, quantum constraints, causal horizons, focusing theorems, radiation, instabilities. Each one a different layer, each one independently derived, the whole system far more robust than any single principle could be alone. And here is the consequence that matters most. The failure to build a warp drive has not left physics empty-handed. It has left physics with a map, a detailed, precisely drawn map of how general relativity and quantum mechanics interact in the extreme conditions that faster-than-light travel would require. That map is more valuable than the warp drive itself would have been, because the warp drive would have been a technology. The map is knowledge, and knowledge, unlike technology, cannot be made obsolete by the next discovery. It accumulates, it connects, it generates more of itself. Here is a question worth sitting with long after this story ends. If every serious failure in science turns out to be a disguised measurement, if the places where physics breaks down are precisely the places where it reveals its deepest structure, then what does that suggest about the failures in your own thinking, your own attempts, your own unsolved problems? Which of your apparent dead ends might be from sufficient altitude? A map of something you have not yet learned to read. The universe's immune system is perfect. Its redundancy is total. Its objections to causality violation are principled, independent, and mutually reinforcing. This should, on first inspection, feel like a prison sentence, a confirmation that the stars are permanently beyond reach, that the scale of the cosmos is a fact of life that no cleverness can overcome. But the deeper you look at what those objections actually protect, the more the feeling changes. Because what the speed limit is defending turns out not to be a restriction on what we can do. It turns out to be the precondition for everything that exists. There is a thought experiment worth doing carefully, because its conclusion is not obvious and its implications reach further than the question itself suggests. Suppose the speed of light were not a limit. Suppose space-time were freely malleable, that any geometry could be produced with available energy, that causal horizons did not form, that quantum mechanics placed no restrictions on negative energy, that the focusing theorems did not hold, that faster-than-light travel was not merely theoretically possible, but practically achievable. Suppose all the barriers explored in the preceding parts of this story simply did not exist. What kind of universe would that be? The instinctive answer is a better one, a universe where the stars are reachable, where civilizations separated by light years can communicate in real time, where the cosmic isolation that defines the human condition dissolves into something more connected, more navigable, more hospitable to life and intelligence across vast distances. But the instinctive answer is wrong, because the properties that make faster-than-light travel impossible are not separate from the properties that make complex, stable, life-supporting reality possible. They are the same properties seen from different angles. Begin with causality. The reason faster-than-light signals destroy causal order, the reason they allow effects to precede causes in some reference frames, is that space-time has a specific geometric structure in which time-like and space-like directions are fundamentally different. Time has a direction. The past is distinct from the future. Events are ordered. This structure is not a decoration added to an otherwise neutral framework. It is the framework. It is what makes the word before meaningful. what allows the concept of process to exist, what permits the evolution of any system from one state to another in a consistent and predictable way. Chemistry requires this. A chemical reaction is a sequence of events, reactants approach, bonds form or break, products emerge. The sequence has an order. Cause precedes effect at every step. Without that ordering, the concept of a reaction of any process unfolding in time becomes incoherent. There is no before and after. There is no reaction. There are only configurations of matter with no narrative connecting them. Biology requires this even more deeply. Life is not a static arrangement of molecules. It is a dynamic process sustained by countless interlocking chemical reactions, each one depending on the outputs of previous reactions, each one feeding forward into subsequent ones. The entire machinery of a living cell operates on causal chains. Signal received, response triggered, product synthesized, structure built or destroyed. Remove the reliability of causal ordering and the machinery stops. Not because any individual molecule changes, because the concept of one thing reliably leading to another no longer holds. Evolution requires this most profoundly of all. Natural selection operates on the principle that heritable variations that improve reproductive success persist across generations while those that do not are filtered out. This requires that organisms with beneficial traits actually survive long enough to reproduce, that there is a reliable causal pathway from trait to survival to reproduction to inheritance. In a universe where causal ordering is unreliable, where effects can precede causes, where the outcome of a process can occur before the process begins, selection has no stable material to work with. Evolution cannot operate. Complexity cannot accumulate. Life in any recognizable form cannot persist. The speed of light, by enforcing causal order at every scale, is not restricting life. It is the precondition for life being possible at all. Now consider the energy conditions, the mathematical requirements that positive energy focuses space-time and that negative energy cannot accumulate freely. These conditions feel from the perspective of warp drive engineering like obstacles. They prevent the geometric configurations that would enable faster than light travel, but they simultaneously prevent something else, the spontaneous and uncontrolled distortion of space-time by random fluctuations in energy density. In a universe without energy conditions, quantum vacuum fluctuations, the ceaseless microscopic variations in energy that fill all of space would have no constraints on their ability to curve space-time. The vacuum would not be a stable background. It would be a churning, unpredictable landscape of random geometric distortions, space-time bubbling and warping at every scale in response to unconstrained energy fluctuations. The atoms that make up ordinary matter could not maintain stable structures within such an environment. Electrons could not occupy reliable orbitals. Molecules could not form. The periodic table would be a theoretical abstraction with no physical instantiation. The energy conditions that make the warp drive impossible are the same conditions that make atoms stable. The quantum inequalities that limit negative energy are the same constraints that prevent the vacuum from dissolving the material world. The focusing theorems that prevent geodesic divergence through positive energy are the same theorems that allow gravity to collect matter into stars and planets in the first place. And then there is the deeper question, one that connects the speed limit to the silence of the universe in a way that reframes both. For decades, physicists and astronomers have grappled with what is known as the Fermi paradox. The Italian physicist Enrico Fermi, during a casual conversation over lunch in 1950, crystallized a puzzle that had been lurking in the background of scientific thinking. The universe is vast, it is old, and the conditions for life appear to be common. By statistical reasoning, technological civilizations should be numerous. If even a small fraction of them develop the capacity for interstellar travel or communication, their presence should be detectable across cosmic distances. And yet we detect nothing. The universe on every frequency we have listened to and every direction we have searched is silent. Many explanations have been proposed. Perhaps life is rarer than we think. Perhaps civilizations destroy themselves before reaching interstellar capability. Perhaps the distances are simply too great for any signal to have reached us yet. Perhaps we are looking in the wrong ways at the wrong frequencies, with the wrong assumptions about how a technological civilization would announce itself. But the warp drive research adds a new dimension to this puzzle, one that is less often considered. Every civilization in the universe, regardless of its biology, its history, its values, or its technological level, inhabits the same space-time, operates under the same physical laws, encounters the same energy conditions and quantum constraints and focusing theorems, faces the same causal horizons and the same Hawking-like radiation at the same geometric boundaries. The speed limit is not a human problem or an Earth problem. It is a universal condition applying with equal force to every concentration of matter too complex enough to ask questions about it. If the barriers to faster-than-light travel are as deep and as structurally embedded as the preceding exploration suggests, if they reflect not a temporary technological limitation, but a fundamental feature of how space-time is constructed, then every civilization in the universe faces them. Every civilization that has ever existed or will ever exist has encountered or will encounter the same set of independent objections from the same set of physical principles. And every civilization has or will arrive at the same conclusion: the stars are not easily reachable. The universe is not designed for rapid transit between its parts. The silence from this perspective is not evidence of absence. It is evidence of a shared condition. Every civilization is in effect marooned on its own island of space-time, not because they fail to find the right technology, but because the ocean between the islands is governed by laws that apply universally and make rapid crossing impossible for everyone equally. This does not fully resolve the Fermi paradox, but it changes its texture. The question shifts from why has no one come to visit us to whether the universe's architecture might by design or by consequence preserve the separateness of its various islands of complexity. Whether the speed limit serves not just to protect causality and stabilize matter, but to maintain a kind of cosmic structure in which each center of intelligence develops in relative isolation, shaped by its own local conditions without being overwhelmed or homogenized by contact with others before. It has had the opportunity to become fully itself. The speed of light in this reading is not a wall, it is a grammar. It is the rule structure that makes the universe's sentences coherent, that prevents them from collapsing into noise, that allows meaning to accumulate at local scales, that gives each part of the universe the time and space to develop its own complexity before being dissolved into the larger whole. Grammar is not a restriction on expression. It is the precondition for expression. A language without grammar is not a freer language. It is not a language at all. It is sound without structure, symbol without meaning information, without the architecture that makes information intelligible. The grammar does not limit what can be said. It makes saying anything possible in the first place. The speed of light is the grammar of physical reality, the constraint that makes structure possible, the rule that keeps atoms stable, chemistry coherent, biology viable, causality reliable, and the universe itself, a place where questions can be asked and sometimes answered. If limits are what make meaning possible, if the boundary is what gives the space inside it, its character, and its coherence, then what does that suggest about the limits you carry with you, the ones that feel like walls, the ones you have been? Pressing against certain, they represent the edge of what is possible, rather than the architecture of what makes you what you are. And now, with that question still open, we arrive at the final turn of this story. Not at a conclusion, because this kind of story does not conclude. It arrives at a vantage point, a place from which the entire landscape becomes visible at once. What we tried, what we found, what it means, and where the path leads from here. Not toward the stars necessarily, but towards something that may in the long run matter just as much. There is a particular kind of journey that does not end where it was supposed to go and arrives somewhere more important instead. The expedition to reach the Northwest Passage pursued by European explorers across 3 centuries of frozen failure never found the commercial shipping route it was looking for. What it found instead was the Arctic, the geography of the polar north, the behavior of sea ice, the limits of wooden ships in extreme cold, the survival requirements of human beings in temperatures that had no precedent in any explorer's experience. None of that was the goal. All of it became the foundation of polar science, of Arctic navigation, of climate understanding that centuries later would prove essential to comprehending the planet itself. The warp drive program has followed a similar arc. The goal was a working faster-than-light drive. What the program produced instead was something more durable, a detailed, rigorously derived map of the boundary conditions of physical reality. A precise description of where general relativity and quantum mechanics converge, where they interact, where their combined constraints become most severe, and what those constraints reveal about the deepest structure of the universe. That map is not a consolation prize. It is the real discovery. Consider what the decades of warp drive research actually produced in terms of concrete scientific knowledge. The exploration of exotic matter requirements forced physicists to develop much more sophisticated theories of quantum vacuum energy, of what the vacuum actually contains, how its fluctuations behave in curved spacetime, and what the mathematical relationship is between the geometry of space and the energy density of the fields that inhabit it. These are not peripheral questions in physics. They sit at the intersection of the two greatest theories of the 20th century, in exactly the region where a complete theory of quantum gravity must eventually be constructed. The Warp Drive program explored that intersection more thoroughly than almost any other research agenda, precisely because it required solutions that pushed both theories to their limits simultaneously. The quantum inequality research, the body of work establishing how much negative energy can exist for how long, under what geometric conditions, emerged, largely from the need to assess the feasibility of exotic matter for warp and similar configurations. That body of work now stands as a significant contribution to quantum field theory in curved spacetime, independent of any application to propulsion. It illuminates the behavior of quantum fields in the presence of strong gravitational gradients in the vicinity of black hole horizons in the early universe, when spacetime curvature was extreme. The warp drive was the motivation. The fundamental physics was the result. The causal structure analysis, the precise mathematical description of how horizons form in superluminal geometries, how information propagates across causal boundaries, how quantum effects behave near those boundaries fed directly into the spheres, theoretical understanding of black hole horizons and their associated thermodynamics, Hawking radiation, the information paradox, the holographic principle, all of these deep problems in theoretical physics are illuminated in part by the same mathematical tools that were developed to analyze why the warp bubble horizon prevents navigation and generates destabilizing radiation. The questions share structure. The answers share mathematical ancestry. This is not an accident. It is the natural behavior of theoretical physics when it is working well. A question asked, in one context developed rigorously enough, produces tools and insights that become applicable across an entire landscape of related problems. The question does not need to be answerable to be valuable. It needs only to be precise, seriously pursued, and followed wherever the mathematics leads. History has recorded this pattern often enough that it deserves to be taken seriously as a principle rather than a coincidence. In the 19th century, physicists were obsessed with the ether, the invisible medium through which light was assumed to travel, the fixed reference frame that would make Maxwell's equations fully coherent and restore the Newtonian picture of absolute space and time. The search for the ether was not frivolous. It was motivated by genuine theoretical need and pursued with extraordinary experimental precision. Michelson and Morley built the most sensitive interferometer of their era, specifically to detect ether drag. They found nothing. The search failed completely. And from that failure, Einstein constructed special relativity. The null result of the Michelson-Morley experiment was not a dead end. It was the key measurement. The failure to find the ether was the discovery that the ether did not exist, and that its non-existence required a complete reconception of space-time and the nature of physical law. The search for something that was not there produced the framework that replaced it. Earlier still, the alchemists of medieval and Renaissance Europe spent centuries searching for the philosopher's stone, a substance believed capable of transmuting base metals into gold, curing all disease and extending human life indefinitely. They never found it. The search was, by any reasonable measure, a failure. But the practical chemistry they developed in pursuit of it, the apparatus, the techniques, the systematic observation of how substances behave, when heated, dissolved, combined, and separated, became the empirical foundation of modern chemistry. The failure to find the philosopher's stone built the laboratory practices that made the periodic table possible. The pattern repeats a goal that was not reached, a search that failed on its own terms, and a residue of knowledge that proved more transformative than success would have been. The warp drive belongs in this tradition. It has not delivered a working faster-than-light spacecraft. It has delivered a generation of physicists who understand the deep structure of space-time, quantum fields, incurved backgrounds, causal horizons, and the relationship between energy conditions and geometric stability at a level that would not have been reached by any less extreme interrogation of the Pop's theory. The universe was pushed hard, and it pushed back in ways that revealed its architecture. Meanwhile, the practical work of reaching the stars has not stopped. It has simply followed the paths that the universe has not blocked. Laser sail propulsion, the concept of accelerating an extremely lightweight spacecraft using the radiation pressure of a powerful ground-based laser array, has moved from theoretical proposal to funded research program. The Breakthrough Starshot initiative, announced in 2016, proposed accelerating gram-scale probes to approximately 20% of the speed of light using a laser array on Earth's surface. At that speed, a probe could reach the Alpha Centauri system in approximately 20 years. The challenges are immense: building a laser array of sufficient power, designing a sail that survives the acceleration phase, developing electronics small enough and robust enough to function as a scientific instrument at gram scale, and solving the communication problem of transmitting data across 4 light-years with a transmitter the size of a postage stamp. None of these challenges violates any physical law. Each of them is an engineering problem, not a theoretical impossibility. Antimatter propulsion remains theoretically the most energy-dense propulsion mechanism physically achievable within known physics. Matter-antimatter annihilation converts 100% of the combined rest mass into energy. No chemical reaction, no nuclear reaction, no conceivable alternative comes close to that efficiency. A spacecraft powered by antimatter annihilation could in principle reach significant fractions of the speed of light without requiring infinite energy, because it is not trying to reach the speed of light, but rather to exploit the maximum energy density that ordinary physics permits for macroscopic propulsion. The obstacle is production antimatter is generated only in tiny quantities by particle accelerators at extraordinary energy cost and stored only with extreme difficulty. But the obstacle is technological, not theoretical. Interstellar hibernation, the concept of placing a crew in a state of dramatically reduced metabolic activity for the duration of a multi-generational journey, addresses the human timescale problem without requiring faster-than-light travel. A journey to Proxima Centauri at 10% of the speed of light takes approximately 42 years. If the crew spends most of that time in hibernation, the biological experience of the journey shrinks to something survivable. The technology does not exist at the required level today. Research on therapeutic hypothermia in medicine has demonstrated that human metabolism can be significantly reduced for short periods without permanent damage. The gap between hours of therapeutic hypothermia and decades of interstellar hibernation is large. It is not obviously unbridgeable. The wormhole concept, a topological shortcut through space-time, connecting two distant regions through a path shorter than the distance between them in ordinary space, remains mathematically valid within general relativity and faces many of the same exotic matter problems as the warp drive. But its theoretical structure is different in important ways, and the research programs addressing wormhole stability and energy requirements are producing results that do not simply replicate the warp drive dead ends. The geometry is different. The constraints are different. Some of the problems that prove fatal to the warp drive are less severe in wormhole configurations. The solution space has not been fully explored. None of these paths is easy. None guarantees arrival. Each requires either physics that does not yet exist or engineering at scales that dwarf anything humanity has built. But each path is real. Each is being actively pursued by researchers who take the problem seriously and approach it without the assumption that the answer must resemble what science fiction has already imagined. And underneath all of these specific proposals runs a deeper current, the recognition that the universe has been showing us through 30 years of warp drive research exactly what kind of place it is. Not a place that yields easily to the desire for fast answers or convenient shortcuts. A place of extraordinary depth, internal consistency, and structural integrity. a place whose rules are not arbitrary impositions, but load-bearing features of a coherent reality. A place that rewards serious engagement not by granting wishes but by revealing its own architecture in greater and greater detail to anyone willing to press hard enough against its limits. The speed of light still stands, not weakened by the decades of theoretical assault launched against it, not revealed as provisional or approximate or subject to revision with the right clever approach. If anything, it stands more firmly now than it did before. Alcubierre wrote his paper because now we know not just that it holds, but why it holds, how many independent physical principles conspire to enforce it, and what the universe would have to sacrifice to abandon it. The limit is not a sign of the universe's stinginess. It is a sign of its depth, of how many things depend on it, of how completely the architecture of reality is integrated around it. To stand at the edge of what physics currently permits and look outward toward the stars is not to stand at a wall, it is to stand at a shoreline. The ocean is real, the far shore exists, the distance is not imaginary, and the crossing is not impossible in principle, only demanding in ways that have not yet been met, requiring knowledge that has not yet been assembled, and perhaps eventually approaches that have not yet been conceived. The stars are still there, every one of them. Proxima Centauri at 4.2 light-years, the Pleiades at 440 light-years, the center of the Milky Way at 26,000 light-years, the Andromeda Galaxy at 2.5 million light-years, all of it real, all of it physically present in the same universe as the planet you are standing on. Separated by distances that the speed of light makes honest distances that cannot be wished away, but that cannot be made impossible either, because nothing in physics says a journey must be short to be worth taking. The distance is not a wall, it is a question. The most beautiful, the most demanding, the most consequential question the universe has ever placed before a species capable of asking it. Not can you go faster, but how deeply are you willing to understand the place you are trying to leave? How seriously will you take the rules of the road before you ask the road to bend for you? How much are you willing to learn before you presume to travel? Humanity is early in its answer to that question. The warp drive research was one chapter of the answer, not the chapter where the problem was solved, but the chapter where the problem was understood. The chapter that revealed what the problem actually is, how deep it goes, and what kind of knowledge will be required before any of the stars become genuinely reachable. That chapter has been written. The next one is open. Which generation of humanity will be the first to stand on soil that formed around a different star? And do you want to be part of the chain of understanding that makes it possible? Not necessarily the ones who go, but the ones who figure out how. The ones who read the map that has been drawn over 30 years of beautiful, instructive, universe-illuminating failure and find somewhere in its detail the path that all the previous paths were pointing toward without knowing it. The speed of light still stands. The stars still wait, and the distance between them and us is not silence. It is an invitation written in the only language the universe knows how to use, the language of physical law, patient and precise, and deeper than any single generation of curious minds has yet managed to fully read. But we are getting better at it, one question at a time, one failure at a time, one layer of reality at a time. That is not defeat, that is how understanding works. And understanding in the end is the only vehicle that has ever reliably closed the distance between what we are and what we might become.